Hi guys, this is Pre-Algebra Lesson 8-4. We're going to make more comparative inferences about populations here, and this is the last lesson of the topic. So pay a real close attention. In this lesson, we'll be able to compare populations using the mean, median, mode, range, and interquartile range, and mean absolute deviation. This is like the ultimate lesson of your statistics topic. So yes, if you don't know what any of these mean, you should go back and review what they are before we start talking about it. All right, let's start with explore it. Jackson and his brother Levi watch Jewel geyser erupt one afternoon. They record the time intervals between eruptions. The dot plot shows their data. Jackson estimates that the average time between eruptions is 8 minutes. Levi estimates that the average time between eruptions is 8.5 minutes. So let's look at the data here. You can see that the Jewel geyser eruptions range between 7 and 9.5. And the mode here, the greatest data that appears would be 8.5. Right, but I would say an even distribution between 7.5 and 9 is clustered in the middle, in the center, right? So construct an argument to support Jackson's position. So we're trying to say Jackson is right. How can we make an argument that could support his argument where the average time would be 8 minutes? So first, we need to figure out if he's using the mean or the median. So let's figure out the mean and the median. So the mean would be 7 plus 7 plus, so all the data together. 7 plus 7.5 plus 7.5. Wait, let's not write everything because that's going to be a lot. So how many sevens? 3 sevens. Plus 1, 2, 3, 4, 5, 7.5. And then 1, 2, 3, 4, 5, 8. And then 1, 2, 3, 4, 5, 6, 8.5. And 4 nines, 2 9.5. So 21 plus 37.5 plus 40 plus 51 plus 36 plus 19 would be 204.5. So how many data do we have? We need to figure out the total numbers of the dots. 3 plus 5 plus 5 plus 6 plus 4 plus 2. That's 10. 20, 25, right? So you divide this, 204.5 divided by 25 is your average, which is going to be 8.18. And so by estimation, maybe Jackson figured out the mean and estimated it as 8 minutes, right? So, or let's see if median would be his argument. Let's see. So 7, we have 7, 1 half, 7, 1 half, 7, 9, 7.5, 9, 7.5, 9. This. Count from the outermost to the innermost. So that would be our median, 8. So that's more accurate, right? So then maybe Jackson is talking about the median. So in order to support his argument, we can say that's the median of the data. Okay, 8 minutes could be the median of the data. So half the time the geyser erupts every 8 minutes or less, The other half of the time, the geyser erupts every 8 minutes or more. Could be his argument. Part B, construct an argument to support Levi's position. So I don't think Levi used either of the mean or the median because 8.5 is not a good estimate for either of them, right? So what else could he have used? What if he's talking about the mode? Because 8.5 is the number that is the greatest, where it comes to how many of data are the same, like appears the same, right? So we can say that in support of Levi's argument, 8.5 minutes is the most, so it occurs most often. And so this means the geyser would most likely erupt again after 8.5 minutes. So those could be, both reasons could be good because they're based on the data and the inferences were made from the data and the measures of variability. Let's look at focus on math practices. How can you determine the best measure of center to describe a set of data? So what is really the best measure of center? Right? We want to consider all of them. And it really depends on the situation and what we want from the data. So we can say that the mean is the average of all the values of a data set, but the mean is affected by the outliers, so maybe it's not the best. So when data has an outlier, the median better describes the center of the data. So if we're just talking about mean and the median, mean could be the best sometimes, but if there are outliers that are like far greater and it's way away from the center of the data, then that really affects the mean to get bigger, right? So like the median would be more accurate in that case. If you see outliers, you want to use median. And we talked about this in the last topic, right? So we're going to make use of that here. So let's look at the next page. Our lesson essential question is, how can dot plots and statistical measures be used to compare populations? Let's look at example 1. We're going to use dot plots to compare populations. Quinn collects data from a random sample of 20 7th grade students who participate in a youth fitness program. She compares the number of curl-ups each student completed in 30 seconds last year and this year. What can Quinn infer from her comparison of the data sets? So last year's data is on top, this year is on the bottom, and she got the data for 20 students, right? So then there are some improvements, there are some non-improvements. We're going to display the two data sets in dot plots to see where most of the spread is, most of the data are, right? So Carl's completed last year has a center around 23 and 24. There's a peak at 24, right? Carl's completed this year, the center has moved higher. So you can already see that this year, students have improved a lot more compared to last year. So if you look at the mode is 24 here, mode is 28 on the bottom, the range is 7 on top, the range is 9 on the bottom, so the variability is greater this year than last year, but because the mode is greater this year, and because you see the cluster mostly in a higher number this year, you can say that this year they're better. So the number of curls completed this year is generally greater than last year, but based on the shape of the data, not all students made the same progress. So Quinn can infer that most, not all, most of her classmates were able to do more curl-ups this year compared to last year. Okay? Let's look at try question. Quinn also collects data about push-ups. Does it appear that students generally did more push-ups last year or this year? Explain your reasoning. So see and compare and contrast the dot plots between last year and this year. And see if you can also answer convince me problem. How does the range of these data sets affect the shape of the dot plots? Pause the video, come back when you're ready for answers. Okay, are you ready? So if you look at the data, the cluster, the shape gives you a peak and where it's usually clustered. So it's more spread out. It's like lower. The shape is lower and more spread out, seems like, this year compared to last year. But the clusters seem to have improved, right? So we can say that based on this data, students generally did more push-ups this year than last year. There are more dots for greater numbers of push-ups completed this year. So how does the range of these data sets affect the shape of the dot plots? Range is the difference between your maximum and the minimum. And so the sample answer would be the data set with greater range is more spread out, right? And the dot plot has a flatter shape, and it has more variability. So it's gonna be spread out more. Let's look at example 2. Use measures of center and variability to compare populations. So Quinn computes the mean and mean absolute deviation, which is MAD, for each data set. How do these measures support Quinn's inference from the data displays? So curl-ups completed last year versus curl-ups completed this year. The mean is 23.6 for last year, and it's 26.6 this year. MAD, what is an MAD? Mean absolute deviation is when you figure out the distance of each point that is away from your mean, and then you figure out the mean of those distances. So it basically represents how far away are they from the mean. And if it's a greater number, that means your data is more spread out on average, right? So if you see the MAD numbers, 1.4 for last year and 2.1 for this year, it tells you that because MAD is greater this year, it means that the data would be more spread out. Like more data would be further away from the mean for this year than it would be last year. Okay, so the mean could be used to describe the data because the data sets do not have outliers. The mean number of curl-ups completed this year is greater than the mean number of curls completed last year. So this supports Quinn's inference. And the mean absolute deviation is greater for this year than last year's, which suggests that not all students made the same progress. So it does support Quinn's inference in example 1. But that's how you can use mean and MADs to make inferences about data. Okay? Let's look at example 3. Use statistical measures to make predictions. Rafi, one of Quinn's classmates, reported the numbers of curl-ups he completed this year and last year. He did not tell Quinn which number is for which year. So based on the data that Quinn gathered, which number most likely represents the curl-ups he completed last year? Based on the data that Quinn gathered here, right? The total curl-ups he got is 19. The total curl-ups he got this year is 23. So he made a progress, right? So So based on the data that Queen gathered, she inferred that most students could complete more curl-ups this year than last year. And so Rafi most likely completed 19 curl-ups last year and 23 curl-ups this year. If you look at the mean, you can also figure out the average data, right? But if you figure out the median, that could also be a representation of the data too. So if Rafi said one is 19 and another is 23, and he doesn't tell us which year were those numbers for, then using the data and using the patterns we see, we can say, yeah, the smaller number would probably be from last year. The bigger number would probably be for this year, right? Let's look at try it. Peter surveyed a random sample of adults and a random sample of teenagers about the number of hours they exercise in a typical week. He recorded the data in the table below. What comparative inference can Peter make from the data sets? So compare and contrast the means and the MAD and make inferences between those two groups, adults and teenagers. See if you can figure out the inference by yourself. Come back when you're ready for answers. Okay, are you ready? So you can see that the mean of teenagers would be greater than the adults. So that means on average, teenagers get more hours of exercise than the adults. But the variability is also smaller compared to the adults, right? So more teenagers, it is more likely that a teenager would get more hours of exercise when they're a teenager versus when they become adults. So one simple answer that you can make inference about this would be that on average, teenagers exercise nearly twice as much as adults. Okay, and that is it for this lesson. Let's summarize our key concepts. So you can use dot plots to make informal comparative inferences about two populations, but dot plots are only accurate when you do not have outliers. You can compare the shapes of data it displays or the measures of center of variability when using dot plots. So mean and MAD. The modes of data set B are greater than the data set A, and the mean of data set B is greater than the mean of data set A. So you can infer that data points are generally greater in data set B here. The ranges and the MADs of the data sets are similar, so you can infer that the variabilities of the two data sets are about the same. Don't forget to use median instead of mean when you have outliers. And the variability, measure of variability for median would be, instead of MAD, would be IQR. So make sure you look at the situation data and see whether or not they have outliers or not. All right, that was it for lesson 4, making more comparative inferences about populations. And that is it for topic 8. We learned about using sampling to draw inferences about populations in topic 8, and it was continued from the last topic. And so hopefully it challenged you to think more statistically and with your data. And so yeah, we'll continue with the next topic, which is topic 9, in the next videos. Thanks for watching, guys. Bye.